Making predictions using probability. So let's go through a thought experiment. Suppose you were to flip a coin 100 times. How many times do you expect the coin to land heads?
Well, if you have heads and tails, right, there's a 50% chance you could land heads or tails. So if I roll 100 times, you'd expect 50 times to go heads.
Does it mean it will land heads this many times? No, right? When you do an experiment, you could get like 30 tails in a row. That's how randomness works. Now, over time, it should get about 50-50, but not necessarily any one moment. So I would say no here. If it does not land heads this many times, it doesn't necessarily mean the coin is unfair. Again, no. When we're talking about randomness, it doesn't stay around 50. It goes on long stretches of doing random stuff. Now, if you're on experimental probability, is this how many times an event happen when you do an experiment over the number of trials? So if we use that formula, we can figure out, well, if I know the probability something is going to happen, and know how many times I'm going to do it, you could guess the number of you could estimate the number of outcomes you're going to have. And the way you do that is the expected value is just you multiply the number of trials n with the probability p. That's all we did. We got our formula here. We went, hey, this is the way you find probabilities by doing what you expect to happen based on mathematics over a number of trials. Rearrange it, you get this formula. So that's how you find the expected value of something. Now, in most cases, the expected value would not be an integer. It would therefore be impossible to actually get the expected value. Is this a problem? Not really. Remember, expected values, we're just doing the expected value, like the assumption, the approximation of it, not the actual things. We're not running a trial here. So let's go through a couple examples. In his basketball career, Michael Jordan, best ever, made 83.53% of his shots from the free throw line. If he had played one more game and had 18 attempts from the free throw line, how many shots would you expect him to make?
Well, our formula is expected value of x is just n times p. In this case, we expect him to shoot 18 shots and make with a probability of 83.53%. So let's move that to a decimal, 0.8353. We'll apply these together and we get about 15.0354. So approximately 15 shots for the free throw line is what we expect to make based on his historical perspective. Okay, last one here. A test to detect cancer is not reliable. It gives a positive result 95% of the time if the person does have cancer. It gives a positive result 3% of the time if the person does not. Probably that around select person has cancer is 0.02. Given that a test on a randomly selected person is positive, find probably that he or she does have cancer. So it might be one to make a tree diagram. So you could either have cancer, you can not have cancer. Right, odds of someone actually having cancer is 0.02. I know it's a sad story, I don't want to really delve on it. 98. This one is cancer. Okay, so probably have cancer is 0.02. Probably they don't, will be the 1 minus out 0.98. Now look what it says. If you do have cancer, it gives you a positive result 95% of the time. So that means a non-positive result 0.05% of the time. If you don't get cancer, it gives you a positive result, if you don't have cancer, 3% of the time, so 0.03. And it'll give you a not cancer 0.97. So look at the first question here. Given that the result of a random submission is positive, so probability given that positive, probably that he or she does have cancer. So it's cancer given that they got a positive result. So all we're going to do is use the formula. So formula here is cancer and positive over positive. So cancer and positive is the straightforward one. It says cancer and positive. This is going to be 0.02 times 0.95. Positive, remember when you want to find positive, it's how do you get positive? How do you get there? Well, do this line, or you get here by doing this line. So it's both those lines together. It is 0.02 times 0.95 plus 0.98 times 0.03.
Plug in our calculator.
And we get 0.39256. It's about 0.39%.
So remember what that means. Given that person was randomly selected had a positive test, what's the odds that they have cancer? About 39%. Again, this is just a math problem. I'm not going to further, but so that's what this thing here says. Next one. Out of the 5,000 people on which the test is used, how many people with cancer would you expect to be correctly diagnosed? So this is a classic IB problem. What I mean by that is, right, A was find this result, which is if you got a positive result, what's the odds you have cancer? And then B says out of 5,000 people on which the test was used, how many people with cancer would you expect to be correctly diagnosed? So first we have to figure out how many people would have cancer from this amount. And they tell us there's about any grouping is about 0.02%. So you have for 5,000 or multiply that by 0.02. And if you do, they get 100. So 100 people have cancer. Now if you have, what's probably you got a correct diagnosis, you got a positive result. So we want to figure out the probability that positive given cancer is what we're looking for, right? What's the odds you got a positive result given that you have cancer? Then we can multiply it by how many people should have cancer. See what we get. So that formula there is just positive and cancer over cancer. Now positive and cancer we did earlier, so this is a classic IB. That was 0.02 times 0.95. And then cancer, well, cancer is 0.02. So these cancel out and you just get 0.95. So 0.95 out of 100, I should almost forgot, right? We multiply by how many people we have, 0.95 out of 100, which is 95 people. So out of 5,000 people on which test, how many people with cancer would you expect to be correctly diagnosed? About 95 people with cancer I would expect to get correctly diagnosed. So it's missed 5 people. Alright, that's the lesson.